Hello everybody and welcome to this A-level chemistry explanation video. What we're going to be focusing on today is titrations and titration calculations. We will be looking at what titrations are actually for, why do we do them. We'll look at how you actually do a titration because you need to know that method inside out. And finally, we'll take a look at how you actually analyse the results you get during a titration. A titration is carried out to determine an unknown concentration for a solution. A solution is where you take a solute and you dissolve it in a solvent. Typically, the solvent is water. The concentration for a solution quantifies the amount of solute that is dissolved in a unit volume of that solution. So for instance, on the left-hand side here, I've got a solution which is in a beaker, which is mostly going to be water, and I'm drawing a couple of particles to symbolise the solute that is dissolved in the solution. Solutions are typically measured in moles per cubic decimetre, and so let's say this solution on the left is 0.2 moles per cubic decimetre. And then the beaker on the right has got a different concentration, and I'm symbolising that by drawing more of these particles dissolved in the water, but also the number. There are twice as many of these particles, so the concentration is 0.4 moles per cubic decimetre. So we've got double the concentration because there are double the number of particles dissolved in a unit volume. Concentrations are typically measured in moles per cubic decimetre, but they could also be measured in grams per cubic decimetre as well. And so the one on the left might be 0.8 grams per cubic decimetre, where the one on the right might be 1.6 grams per cubic decimetre. This isn't telling us the precise amount of substance that we have in our beaker, but what it is saying is if we had 1 decimetre cubed or 1 litre, we would have 0.2 moles of that substance. So it is a per decimetre cube. This is an amount of substance per unit volume. The titration reaction itself takes place in a conical flask, which takes its name literally from the fact that it is a cone-shaped flask. What you do is you add a known volume of a solution to the conical flask using a pipette. These aren't like the normal dropping pipettes. These are specifically, they only have one line on them. And when you have a solution in the pipette up to that line, you know you have a very specific volume, typically 25 cm cubed or 10 cm cubed for titrations. Once you've transferred your solution into the conical flask, you set up a burette clamped in position above the conical flask. This has got the other chemical in it that you're going to react with whatever is in your conical flask. Typically, titrations are a reaction between an acid and an alkali, but there are other types of titration. There's no rule for which chemical goes in the conical flask and which goes in the burette. For this example, I'm going to say acid is in the burette and alkali is in the conical flask. I'm also going to say that it's alkali that I'm finding out the concentration of. Typically, the unknown concentration goes into the conical flask, but it doesn't need to. It does work both ways. The solution that you already know the concentration of, the one that I'm saying is in my burette, is called the standard solution. And it's called that because you're going to be using it to find out about the other solution. The reaction between the acid and the alkali, or base, as sometimes alkalis are referred to as, is called neutralisation, of course. And what's happening is the acid and the base are cancelling each other out to make a neutral solution. But usually we won't know that this has happened without adding some kind of indicator to the mixture. And this will change colour once the correct volume of acid has been added to the burette. And then, to make sure that the colour change is really obvious, we place a white tile underneath the conical flask. Just before we start the titration, we must note down the volume reading on the burette. When the burette is full, the reading will be 50.00 cubic centimetres. You don't need to start the titration with the burette being totally full, but often that's what people prefer. Then what you do is you add alkali from the burette by opening the tap. You swirl the conical flask whilst you do this. This ensures a thorough reaction. And this is why we choose a conical flask for the reaction itself. Its shape means that you can really swirl that reaction mixture from side to side without spilling any of it. As we add the chemical from the burette, the colour of the indicator might change briefly, and then when we swirl the conical flask, the colour might change back. This is completely normal and shows us that the chemicals hadn't been thoroughly mixed at first, and then the colour changed back once they had been. During the titration, we also might rinse down the sides of the conical flask with some distilled water, and this is completely okay, won't affect our titration because the distilled water is not an acid or an alkali. And then we stop our titration by closing that tap when the colour changes permanently. This is called the end point in the titration. Now is the time to reread our burette. The volume of liquid in the burette will have gone down, and so will the number on the side of the burette, because the number that we read tells us the volume of chemical that is still in the burette. And so, for instance, the new reading on the burette might have gone down to 26.80 cubic centimetres. That's how much is left in the burette. What we need to do now is work out the volume of solution that we've added from the burette. This is called the Titre volume. To do this, we need to work out the difference between the starting volume and the end volume. And so if we started on 50.00 and it went down to 26.80, the difference between those two numbers is 23.20 cubic centimetres. The first value that you get in your titration is probably an overshoot, which means it will be too large. And so what we need to do then is repeat our titration and try and do it with a little bit more care. So what we have to do is we wash out our conical flask, or maybe get a fresh one, and do all of this again and to check our result. This time though, what we're going to do is we slow down when we are about 2 or 3 cubic centimetres away from our rough titration that we've done before, our rangefinder it's sometimes called. So you could get up to maybe about 21 cubic centimetres quite quickly, give the mixture a really good swirl and rinse down the sides, but then add from the burette drop by drop, swirling continuously each time to really give yourself the best chance of catching that endpoint to the titration. When you do a titration, it's important to carry out a number of repeats so you can be confident in the conclusion that you make. In order to get that confidence, your results need to support each other by being close enough to each other that you can conclude that they are accurate, in other words, close to the true value. These types of results are called concordant results. Typically, concordant results are taken to be those results that are within 0.10 cubic centimetres of each other. So if we take a look at this titration results table that I've drawn here, you can see that we've got 3 rows. We've got the starting volume, so that's the volume of liquid that was in the burette before we began. Then we've got the end volume, so that's what the reading went down to. And then we've got a row for Titre volumes. Titre volumes are the difference between each reading. And so if you look at the first one, we've got 23.20 is the difference between these two numbers. That's our rough value. The next one, the difference is 22.40. The next one, the difference is 22.30, then 22.55, then 22.30. So we've done a total of 5 titrations. The first one was too big because we didn't know exactly what we were aiming for. The other 4 are quite close together. However, this reading number 4 for the Titre volume, 22.55, is a little bit too large. Looks like we overshot somehow again. So we've got 3 concordant results, 3 results that are all within 0.10 of each other. They are concordant. So when we are trying to work out what our mean Titre volume is, we must only use these concordant results to calculate our answer. So we calculate the mean in the way that we normally do. We just exclude these two results that are too big. So we do 22.40 plus 22.3 plus 22.3 all divided by 3, which gets us 22.33 cubic centimetres, still reporting this to 2 decimal points. There are two indicators that you need to know the colour for to be used during titrations. The two indicators are methyl orange and phenolphthalein. Methyl orange is red in acid and yellow in alkali. So at the end point of our titration, it will go orange. Phenolphthalein is colourless in acid and it's pink in alkali, and so you end your titration in one of two ways depending on what you're adding to the conical flask. If you're adding alkali to the conical flask, you stop when the colour goes pink, just. And that's because all the alkali has been used up and you've added 1 drop of alkali to get the alkali colour. If you're adding acid to your conical flask, you will stop when it goes just colourless, because all of the alkali has now been used up. In a way, phenolphthalein is a more easy to use indicator because it is one colour or the other. But in some respects, it's easier to overshoot without knowing, which is why repeated experiments are important to allow us to know if we've done a significant overshoot, in which case we can ignore that reading from our final mean Titre. Using methyl orange and aiming for an orange colour carries its own difficulties though, because we're aiming for orange, which is obviously the colour that you get when you mix red and yellow. But there are various possible shades of orange, so the important thing here is to be consistent from one titration to the next, and that's how you ensure concordancy. Sometimes you don't actually have any choice about which indicator you need to use. If you're working with a strong acid, you should choose methyl orange. A strong alkali, you use phenolphthalein. You only have a choice when you're using both a strong acid and a strong alkali, and then you can use either. When you analyse a titration, we are obviously going to have to do some calculations involving concentration. Remember, concentration is an amount of substance in a solution, and it's measured in moles per cubic decimetre. That's all important because that allows you to work out the relationship between concentration, moles and volume, because concentration must be equal to moles divided by volume in cubic decimetres, because that's literally how you would write as a fraction moles per cubic decimetre. More usefully, the relationship, I think, can be expressed as moles is concentration multiplied by volume. I prefer this one because it's more easy to rearrange it and make concentration and volume the subject of your calculation once you've got those numbers put in. Since concentration is in moles per decimetre cubed, I've said that volume must therefore be in decimetres cubed. To be annoying, exam questions sometimes challenge you by giving you the volumes in cubic centimetres, and so what you have to do is you have to convert it yourself. Since there are 1000 cubic centimetres in 1 cubic decimetre, all we need to do to turn cm cubed into dm cubed is divide by 1000. So 25 cubic centimetres will be 0.025 cubic decimetres, and 50 cubic centimetres will be 0.05 cubic decimetres, etc. Now, I did mention earlier that concentration is typically in moles per decimetre cubed, but it can be expressed in grams per cubic decimetre. And so what you might be required to do is calculate a concentration in moles per cubic decimetre and then turn it into grams per decimetre cubed yourself. Now, since both of these terms are per cubic decimetre, what we're really being asked to do is change moles into grams, or more specifically, mass. And since we know that mass equals mR times by moles, we can therefore say that what we need to do is turn our moles per decimeter cubed into grams per decimeter cubed by multiplying by the mR. And that's what you need to do. You need to remember that moles per cubic decimeter multiplied by the mR of whatever solute is dissolved in it is going to be turning that concentration into grams per cubic decimeter. When you are analysing your titration results, the core concept can be observed just by looking at our setup. If we've got our acid in our burette and we know the concentration of the acid, we add a certain Titre volume of that acid to the conical flask. What we know now is the concentration of the acid and the volume of the acid required to neutralise our alkali. So we've got the concentration and the volume. So step one in a titration analysis is how many moles did I add from that burette? And so to work that out, we do moles is concentration times by volume. Step two is to use the equation for the reaction to work out the moles of the other chemical that there must be in the conical flask. And so that means use the ratios, use those numbers, the coefficients in the equation. Is it 1 to 1 or 1 to 2? We'll look at some examples of that in a moment. And the third and final step is, well, I know what volume of solution I'd put in my conical flask. I now know what moles I've got of that alkali. And so the final step is, well, what is my unknown concentration? And since concentration is moles divided by volume, that will be our final step in the analysis. The best way to analyse a titration is to use something called the grid method. And this method involves structuring the information that you're given in the question in a particular way that's really easy to reproduce from one question to another. So for instance, if we take a look at a titration where 25 cubic centimetres of sodium hydroxide is put in a conical flask, we don't know the concentration of this sodium hydroxide. Then we put hydrochloric acid in the burette, the acid's concentration is 0.1, and we add the hydrochloric acid from the burette until we get neutral being displayed by our indicator. We've been presented with an equation for the reaction. You can see that sodium hydroxide reacts with hydrochloric acid in a 1-to-1 ratio, and we know that because there are no numbers in the equation. Everything is 1-to-1. The grid has got the following side headings. We've got chemicals on the left-hand side, the top row. And this is always the two chemicals that are in the conical flask and the burette. Doesn't matter which way round you put them. Let's put the hydrochloric acid here and the sodium hydroxide here. And then our next headings are concentration in moles per decimeter cubed, volume in decimeter cubed, moles, and then mole ratio. Now let's tackle that first. The mole ratio is simply the coefficients, the multipliers that are in the equation. Remember, there are no numbers here, so these are both 1. What that means is 1 mole of sodium hydroxide requires 1 mole of hydrochloric acid to react with it. Then if we put the rest of our information into the table, we know that the hydrochloric acid concentration is 0.1. We don't know what the sodium hydroxide concentration is. That's our goal. The volume of hydrochloric acid is 20 cm cubed, which means it's going to be 0.02 dm cubed. And sodium hydroxide, similar, 25 cubic centimetres, so 0.025 cubic decimetres. So now we've put all of the information we've been given into the grid, you can see that there are a few things that we don't have. First of all, the moles of hydrochloric acid. That's job 1. Moles is concentration multiplied by volume. So our 0.02 multiplied by 0.1. And so that is going to give us 0.002 moles of hydrochloric acid. Now our ratio comes into play. 1 mole of this reacts with 1 mole of this. In other words, these 2 moles are going to be the same number. Whatever the number of moles is, they have to be the same because it's a 1-to-1 ratio from the equation. So this will be 0.002 as well. Then our final gap and our ultimate goal is to work out the concentration of sodium hydroxide. Since concentration is moles divided by volume, we're going to do 0.002 divided by 0.025, which is going to give us 0.08 moles per cubic decimeter as our final answer. We can always do ourselves a little reasonableness check. If we take a look at these two volumes, they are 20 and 25. Since the mole ratio is 1:1, it must be the case that the sodium hydroxide is a little bit less concentrated because we needed a bit more of it in order to cancel out our hydrochloric acid. So 0.08 is a little bit smaller than 0.1, so we can be confident we've got the right answer. We're just going to take a look at one more example. It's a more difficult example because the mole ratio from the equation is different. In this example, let's say we've got 25 cubic centimetres of potassium hydroxide of an unknown concentration in the conical flask, and in the burette we have sulfuric acid this time, and we add that sulfuric acid, which has got a concentration of 0.05 moles per decimeter cubed, into the conical flask, swirl it until the indicator changes colour. We set our grid out in the exact same way, the exact same side headings. We'll put our potassium hydroxide here and our sulfuric acid here, and the concentration of sulfuric acid is 0.05. The volume is 30 cm cubed, so 0.03 dm cubed, and so our moles is going to be concentration multiplied by volume, so 0.0015, or we could have it in standard form, 1.5 times 10 to the minus 3. Both of those completely fine. The mole ratio from the equation says that we need 2 potassium hydroxide for every 1 sulfuric acid. So those ratios need to go in here. And what that means is, however many moles of sulfuric acid we've got, we will need double the number of moles of potassium hydroxide. So we need to double this value that we've just calculated, and that will turn it into 0.03 moles of potassium hydroxide. Again, could be in standard form. And so our final goal to work out the concentration of potassium hydroxide is to take our moles that we've just worked out, divide it by our volume, 0.025 dm cubed, and we get our concentration. And this time the concentration is 0.12 moles per cubic decimeter. And again, this number seems reasonable because we need twice the moles of potassium hydroxide that we need for sulfuric acid, and we are using a smaller volume. And so the concentration needs to be more than double to compensate for that. Okay, that's the end of this video. I'll see you again soon.